In the last few videos, when talking about simple harmonic motion, we have found this solution here. So this is the solution to the equation of simple harmonic motion. And we have discussed a different aspect of this solution and different characteristic of it at length. And as a demonstration, here I have plotted this solution for one of the special cases. So this specific graph is a plot of the equation x of t equal to sine of 6t. So from this equation, it's clear that the amplitude is 1, the angular frequency is 6, and the phase constant is 0 for this plot. So along this axis, we have the time axis. This is the axis which plots x. This is +1, which is the value of the amplitude, and this is -1. And as you can see, in a single second, the motion that's been represented here makes approximately 6 radian, not approximately, exactly 6 radian, in about 1 second. For the sake of remembrance, let me mention the equation of motion for simple harmonic oscillation, and that was given by this: the double time derivative of x plus omega naught squared x equal to 0. And the solution is a sinusoidal solution, and this is the plot of a sinusoidal function, and it goes on like this for the rest of the time. However, in reality, whenever we have experimented with spring or any oscillatory system, we clearly know that this is not the case. Not at all time the system maintains its motion. In reality, the system dissipates a lot of energy with time, and eventually it stops and comes to an equilibrium position. And if you have to keep up the motion, you'll always have to feed energy into the system so that the energy can go on as long as you keep plugging in energy into the system. So that is the basic premise of reality. And physics is a science that's based on reality, based on experiment, based on the nature. And of course, it will have to account for this dissipation of energy and the resulting motion thereof. So in order to represent the true motion, we can start to make amends to this equation of motion and our concept of harmonic oscillation. And to sort of show you what the real motion look like, here I have plotted a harmonic oscillatory system that eventually comes to a stop. And here we have it. I've also put it against the simple harmonic motion so that the contrast becomes obvious. It's the blue line which represents a motion which is being inhibited. That means, in other words, it is damped, a phrase we are going to use over and over again. And therefore, the amplitude starts to settle down and decreases with time. And if we have continued this graph for long enough, we would see that it eventually comes to a stop for any practical purpose. On the other hand, the ideal system that we have conceived in our mind keeps on oscillating, which is clearly not representative of a real system. So, the big question: what kind of modification we'll need to introduce in our equation of motion so that it starts to account for this damping effect? And that's what this video is about. The term damping is often used in lieu of the plethora of resistive forces that acts around us. So damping refers to resistive forces. Resistive forces. Mathematically, in mechanics, damping is instigated by velocity-dependent forces. And velocity-dependent forces are an interesting bunch. In general, if an object faces drag force in any fluid, almost every time it feels so when it's moving with a certain velocity. So, an object which is stationary will not feel drag force. In general, a drag force on an object which is moving through a fluid is often given by a formula. So if drag is given by a constant times the velocity, so let's call this b1, so negative b1v, and of course f is a vector, minus b2 v squared times v hat, where v hat is a unit vector in the direction of velocity. This could also be written a little differently, albeit equivalently. So we could write b2v magnitude and then multiply it by the v vector. And by necessity, we would require that b1 and b2 are both positive constants. Otherwise, this force would be positive if both were negative, and therefore instead of decreasing the velocity, they would increase the speed, which is not an appropriate consequence of damping forces, or drag forces for that matter. For most practical purposes, b1 constant here is much larger than b2, and of course if the velocity is very small, then this term here becomes much smaller than this one. So oftentimes when we talk about the effect of drag force on simple harmonic oscillator, we consider this term only and ignore this term altogether. Although there are occasions when this needs to be taken into account, but this is not one of those cases. So for us, the drag force is given by F drag is equal to the first term, which is negative b. Since we don't need the second term, let us drop the subscript times the vector v. And for one-dimensional harmonic oscillator, we can consider only the magnitude without considering the direction, because everything points along one direction only. This allows us to write down the Newton's equation of motion, which is F spring plus F drag equal to ma. And this is where we start to implement the dot notation. So something dot would mean the time derivative of it. If we have double dot, that would imply it's been differentiated twice. So being consistent with the notation, we can write it down as follows. The right-hand side of the equation shall be written on the left-hand side as mx double dot. And this is equal to the spring force that we know from the previous videos, which is negative kx. And the drag force, which is of course given by the formula that we have just discussed, which is b times v, but v is of course the first derivative of the position, and therefore b times x dot. So now that we have it, we can divide all the terms by m and bring all the terms to the left side of the equation. That would give us x double dot plus b divided by m times x dot plus k divided by m times x equal to 0. Of course, this is the constant which is familiar to us, and we have so far written it as omega naught squared, so that omega naught is equal to square root of k divided by m. But this constant is new for us, and we'll be defining it as 2 times beta. We have introduced 2 here for a good reason, and that will be apparent as we go along and write down the solution. So this results in the following equation: x double dot plus 2 beta times x dot plus omega naught squared times x equal to 0. And this is the equation of motion for damped harmonic oscillator, but the middle term is the new addition which causes all the damping. It's very important to get the signs of the term right, because if we change this plus sign to a negative sign, then this will cause in results which are not consistent with reality. Instead of damping the motion, it will simply increase the amplitude with time. So this is our equation of motion for damped harmonic oscillator. Now it's time for us to solve it. As evident from the form of this equation, this clearly resembles the definition of linear differential equation that we talked about earlier in this series. And notice that if we had to use x dot squared term in this equation, then this wouldn't be linear anymore. So it's a good thing that we are working in a domain where this assumption is valid. Of course, if we have to work with terms involving nonlinearity, then we'll have to change oscillation appropriately. There are a couple of ways, but the solutions are never nice. In this case, however, we should get a nice solution. So not only this is linear, but this is still homogeneous. We have explained what homogeneity is on that video as well. So I'll be linking that video in this one. So you should see a link appearing right now. And if you haven't seen that video, I'd recommend you to watch that before you keep on watching this. Presuming the fact that you know what to do with linear homogeneous differential equation, this is the appropriate time of mentioning that there is not a very well laid out way of directly integrating this equation in order to get the solution. So we'll have to take the refuge in the method of guessing, which we also mentioned in a previous video, and I'll also be linking that video in this one as well, so that link should appear right now. Assuming the fact that you are familiar with the method of guessing, what that is that we carefully notice that the derivative of the function we're differentiating, which is the position, gives us the lower order derivative, or the function itself, back. And there is one type of particular function which displays this property more than any other function, and that is the exponential function. So for example, if we have e to the power t, and if we differentiate it, we get e to the power t. If we differentiate e to the power some constant, for example r times t, it gives us r times e to the power rt. So equipped with this knowledge, we'll assume that our solution is of this form, And this in turn will produce an algebraic equation, which we'll be calling the characteristic equation, that will be crucial in finding out the explicit solution to this equation. So let us plug in this ansatz, e to the power r times t, where r is presumably a constant. So what do we get? For the first term, we get r squared e to the power rt. From the second term, we get 2 beta r e to the power rt. And for the last one, we get omega naught squared times e to the power rt equal to 0. Since in the known domain we have been working in, e to the power rt is non-zero, this allows us to get rid of this factor here, so we are left with r squared plus 2 beta r plus omega naught squared equal to 0. And this is our characteristic equation. Now this is of course solvable, and we know how to solve it. It's a second degree polynomial in terms of r. So for second order polynomial equation, which looks like ax squared plus bx plus c equal to 0, the solution is written as x equal to negative b plus minus square root b squared minus 4ac divided by twice a. If we apply this formula, then we get, of course, two roots, and those are given by negative b plus minus square root beta squared minus omega naught squared inside the square root. And this is a very neat solution, and this is part of the reason why we took the middle constant to be twice beta instead of beta. So of course, we'll be calling the root with plus as r1, so r1 is negative beta plus square root of beta squared minus omega naught squared, and r2 will be negative beta minus beta squared minus omega naught squared. So these are our solutions, right? And consequently, our two solutions to the differential equation, remember it's a second order linear differential equation, so we should have two solutions with two integrating constants. So our first solution is going to be e to the power negative beta times t times e to the power square root of beta squared minus omega naught squared t. And the second one is going to be the same solution except for a negative sign. So something like this. And of course, the total solution will be a superposition of these two solutions. That means since we have freedom to take two integrating constants, this is where we shall utilize them. So the first constant is a times e to the power square root beta squared minus omega naught squared times t plus b times e to the power square root, of course with a negative sign, beta squared minus omega naught squared times t. And this is our complete solution. The physical meaning of the solution is of course going to be discussed in the next video, so stay tuned. Don't forget to like this video if you have found it helpful, and remember to subscribe. Thank you very much for watching.